Good morning, students. In this video we will discuss Legendre polynomials and their solutions and the Legendre differential equation. So in many problems of mathematical physics and engineering, we find second order linear differential equations whose solutions give rise to special functions like sine functions, cosine functions, exponential, logarithm functions, and many more functions like Legendre polynomials, Chebyshev polynomials, etc. So we will obtain the solution of these type of linear differential equations which define the special functions, and these special functions are defined as Legendre polynomial in the Legendre differential, in case of Legendre differential equations. So firstly, we have this differential equation which is called Legendre differential equation. The equation is given by 1 minus x square into double derivative of y with respect to x minus 2x derivative of y with respect to x plus n into n plus 1 into y is equal to 0. Here this n is any real constant. So this differential equation is called Legendre differential equation. This equation has many applications, and in many of the applications, n, which is a real constant, that takes only positive integer values. So we can write this equation as 1 minus x square into y dash. Here I am denoting this y dash as derivative of y with respect to x. Derivative of this, then n plus 1 y, that is 0. So we can see derivative of this term 1 minus x square into y dash, that becomes these two terms. 1 minus x square as such, derivative of y dash, and then derivative of this with respect to x, which is minus 2x, and y dash as such, by product rule. So now we can see the singularities of this equation are x is equal to plus minus 1, because we have this factor 1 minus x square. So 1 minus x square is 0 whenever x is equal to plus or minus 1. So the singularities of this equation are plus minus 1. That means if we want to find a power series solution about x is equal to 0 of the form let yx, say summation cm xm, m varying from 0 to infinity, this is power series solution of the equation about x is equal to 0 this is the power series solution of equation 1. Then because the singularities are at the point plus 1 and minus 1, so this series will be convergent in the unit disk. That means this series will be convergent for all x where mod of x is less than 1. The series solution will be convergent in this region mod x less than 1, since the singularities are at x is equal to plus minus 1. So let us say yx is equal to this summation cmxm is the solution of this equation. Then what is derivative of y? That will be summation m cm x raised to m minus 1, derivative of this particular portion, and that is from 1 to infinity, because the first term in the summation, that is just a constant term, and when we take derivative, that will vanish. Similarly, the second derivative, that is m minus 1 cm x m minus 2 from 2 to infinity. So now we put these three values y, y dash and y double dash in equation 1, and we get summation m minus 1 cm x m minus 2 So the first term is 1 minus x square into double derivative. That means this double derivative minus x square into double derivative. So that becomes x raised to m minus 2 x into first derivative of y. So that will be m cm x raised to m from 1 to infinity. And then n into n plus 1 into y. And y is summation cm xm from 0 to infinity. So that is 0. Now we simplify this. So we get this thing. When we simplify it, we get 2c2 6c3 plus m varying 4 to infinity m into m minus 1 cm x raised to m minus 2 minus m minus 1 cm x raised to m from 2 to infinity minus 2c1x 2 m cm xm 2 to infinity plus n into n plus 1 into c naught plus c1x plus n into n plus 1 cm xm from 2 to infinity, that is 0. So we have separated from the first sum the terms containing c2 and c3, and then rest of the terms as such. Similarly, from the third sum we have taken the term which contains c1 outside, and then from this summation we have taken the term c which contains c0 and c1 outside. So in the first summation, for this first summation, we put m minus 2 is equal to t. For the first sum, put m minus 2 is equal to t. So this first summation becomes basically m varying from 2 to infinity, m plus 2, m plus 1, c m plus 2 x raised to m. So the whole of this equation becomes basically 2c2 n plus 1 c naught. These are the constant terms which does not contain any x. Then the coefficients of x, 6c3 minus 2c1 n plus 1 c1. Then we have this t varying from 2 to infinity, t plus 2, t plus 1, c t plus 2 x raised to t minus summation from 2 to infinity m minus 1, 2m, n plus 1 into Cm xm, that is 0. So when we simplify the equation, we get all these. These are the constant terms, then term containing x, then these two rest of the summations. Now here this t is a dummy variable. We can replace this t by m. So that means this summation can be written as m varying from 2 to infinity, m plus 2, m plus 1, c, m plus 2, x raised to m. So now we equate both sides. So on the right hand side we have only 0. So this equation will be equal to 0 if and only if all the different powers of x are 0. So we will equate all the different powers to 0. So firstly, the constant term, equating the coefficients of various powers of x on both sides. We get, firstly equating the constant term, we get C2 is equal to minus 1 by 2 n plus 1 C naught. Then equating the term containing x, that means the coefficient of x, we get 6C3, 2C1, n plus 1 C1, that is 0. So we get from here C3 is 1 by 6, 2 minus n square minus n C1, which can be written as 1 by 3 factorial n minus 1 n plus 2 C1. So here we can see by equating constant term we get C2 in terms of C0, and by equating the term containing x we get C3 in terms of C1. Similarly, when we equate coefficient of x raised to m, equating the coefficient of x raised to m, we will get this term m plus 2, m plus 1, cm plus 2 minus m square plus m minus n square minus n cm, this is 0. This thing is true for all m varying from 2, 3 and so on. So from this we will get cm plus 2, that is minus n minus m, m plus n plus 1 divided by n plus 2, m plus 1 cm for all m greater than or equals to 2. So we can see like C2 in terms of C0, C3 in terms of C1, we get Cm plus 2 in terms of Cm here. So from this Cm plus 2 in terms of Cm, by putting m is equal to 2, 3 and so on, we can simply calculate that C4, that is just minus n minus 2 n plus 3 divided by 4 into 3 C2. So this can be written as n minus 2 n plus 1 n plus 3. Now we put the value of C2 here. So we will get 4, 3 into 2 factorial C naught. So putting the value of C2 in terms of C naught, we get this. So that will be 1 by 4 factorial n minus 2 into n plus 1 into n plus 3 C naught. Similarly again in the same formula, put m is equal to 3 and we get C5, and that will be minus n minus 3 n plus 4 divided by 5 into 4 into C3. Again put the value of C3, so we will get n minus 3, n minus 1, n plus 2, n plus 4, C1. So continuing this process, we can calculate all the coefficient Ci's and we get the solution. Now our solution was yx summation Cm xm from 0 to infinity. So we put the values of Cm here. So that will be C0 plus C1x, C2x square, C3x cube and so on. So this will be C0, C1x. Now putting the value of C2 here, that will be 1 by 2 factorial, n plus 1, C0. Then putting the value of C3, we get 1 by 3 factorial, n minus 1, n plus 2, C1 x cube, then plus C4 x raised to 4, so that will be 1 by 4 factorial, n minus 2, n plus 1, n plus 3, C0 x raised to 4, and then next term will be 1 by 5 factorial, n minus 3, n minus 1, n plus 2, n plus 4, C1 x raised to 5, and then so on. So you can we can simplify this as C0 into 1 minus 1 by 2 factorial, n plus 1 x square, 1 by 4 factorial, n minus 2, n plus 1, n plus 3, x raised to 4 and so on, plus C1 into x minus 1 by 3 factorial, n minus 1, n plus 2 x cube, 1 by 5 factorial, n minus 3, n minus 1, n plus 2, n plus 4, x raised to 5, and then so on. So we can write it as C0 into y0 x plus C1 into y1x, where y0 is this function in the bracket and y1, that is this function. So we have found solution of Legendre differential equation in we have found a power series solution about x is equal to 0 yx, that is C0 into y0 plus C1 into y1, where y0 is this function and y1 is this function. Now the series, we know the series yx converges in the area where mod x is less than 1. So the two functions y0 and y1, they will also converge for the same. y0 and y1 converge for mod x less than 1. Now we can notice from this that y0 contains only even powers of x, the constant term, the term containing x square, x raised to 4 and so on, and y1 contains only odd powers of x. So the two solutions y0 and y1, they are linearly independent to each other. Since y0 contains only even powers of x and y1 contains only odd powers of x, so they are linearly independent solutions. That means these two functions give complete solution of Legendre's equation. Now, if we take n to be 0, then what will happen? This is our n, this is y0. So when we take n to be 0, then y0 becomes only 1. If we take n is equal to 2, then y0 becomes 1 minus 3x square. Similarly, when we take n is equal to 4, y0 becomes 1 minus 10x square, 35 by 3x raised to 4, and so on. When we take even values for n, y0 becomes 1 minus 3x square, and so on. But when we take odd values of n, let us take n is equal to 1. When we take odd value, let us say n is 1, then y0 becomes 1 minus x square minus 1 upon 3x raised to 4, and so on. Infinite series. Similarly, when we take n is equal to 3, we get y0 as again infinite series. So here we can see that for the even values of n, y0 is a finite equation, or you can say y0 is a finite sum, and for the odd numbers, odd values of n, we get y0 to be the infinite series. I repeat, when we take n as an even integer, then y0 will be finite sum, and when we take n to be the odd integer, then y0 becomes infinite series. Similarly, for y1, when we take n to be odd integers, let us say 1, then y1 becomes x. When we take n is equal to 3, y1 becomes x minus 5 by 3x cubed. When we take n is equal to 5, then y1 becomes x minus 14 by 3x cubed, 21 by 5x raised to 5, and so on. But if we take even values, let us say 0, for n is equal to 0, y1 will be infinite series, x minus x plus 1 by 3x cubed plus 1 by 5x raised to 5, and so on. So for n is equal to 0, y1 is infinite series. Similarly, for n is equal to 2, this is also infinite series. So we can conclude from here that for any integral value of n, one of the functions y0 and y1 remains a finite sum, and other remains an infinite series. For each integer value of n, one of the two functions y0 and y1 reduces to a polynomial and other remains an infinite series. So the polynomials, for example, when n is 0, y0 is a polynomial. Then when n is 1, y1 is a polynomial. Then for n is equal to 2, again y0 is a polynomial. For n is equal to 3, y1 is a polynomial. And then for 4, this is a polynomial, and so on. So these polynomials, when multiplied by a suitable constant, they are called Legendre polynomials. I repeat, these polynomials, these polynomial values, when we multiply them by a suitable constant, they are called Legendre polynomials. The Legendre polynomials are denoted by Pnx. So we can write like these polynomials multiplied by suitable constants are called Legendre polynomials. And are denoted by Pnx, where n denotes the order of the polynomial. Therefore, we can see when n takes integral values, one of these two linearly independent solutions y0 and y1, that is a Legendre polynomial, and the second independent solution is an infinite series. So we will denote the second independent solution by Qnx. The second solution will be denoted by Qnx. But we have written that the polynomials multiplied by some suitable constants, they are called Legendre polynomials. So we have to evaluate those multiplicative constants. So the value of the multiplicative constants can be obtained by setting Pn at 1 is equal to 1. So we set Pn at 1 is equal to 1, and then we calculate the values for the multiplicative constants, and that we will determine by Rodrigues formula, and that will we discuss in the next video.